Imagine stepping into a car, but instead of sitting in the driver's seat, you sit back as a passenger, and there's no driver at all. The car starts moving, turns corners, stops at red lights, and takes you exactly where you need to go. Sound like magic? It's not magic. It's the amazing world of autonomous vehicles. Also known as self-driving cars, these incredible machines use cutting-edge technology to see the world around them, make decisions, and drive safely without a human at the wheel. In this video, we explore these same principles on a smaller scale using the JetBot autonomous robotics platform. Before we begin, we'd like to introduce our team. Our group consists of Hadif Multazam, Akmal Hazrin, and Matthew Choi. Together, we collaborated on designing, implementing, and testing the autonomous navigation system you'll see in this video. Before we break down the weekly workflow, here is a brief overview of the project background. Throughout this module, our main objective was to develop a small-scale autonomous navigation system using the JetBot platform. Just like a real autonomous vehicle, our robot needed to perform 4 essential functions: understand how to move, interpret visual information, determine its position in the environment, and plan the best route to its destination. The 3 labs we completed were designed to build these capabilities step by step, beginning with motion control, then visual perception, and finally localization and path planning. All of these components were later integrated into a single autonomous system, which we demonstrated in the final week. With that context in mind, here is the workflow we followed across the 4 weeks of the project. Week 1 focused on understanding how the JetBot moves and how to control it accurately. We began by learning basic motor commands in Python, which allowed us to independently control the left and right wheels. This gave us our first insight into how differential drive robots behave. Next, we performed odometry calibration. By measuring the distance traveled at a different motor value, we identified how small differences between the 2 motors caused the robot to drift. We then tuned the wheel bias so the JetBot could travel in a straight line. Finally, we applied inverse kinematics to plan controlled movements. We broke more complex motions into a sequence of straight paths and in-place rotations, allowing us to predict and execute precise maneuvers, such as turning at an intersection. Overall, Week 1 gave us a strong foundation in robot motion, calibration, and trajectory planning, which became essential for all later labs. Week 2 introduced visual perception and control, allowing the JetBot to react to its environment instead of relying solely on predefined motor commands. We started by using the JetBot's camera to detect the yellow path on the mat. By converting the image to HSV color space, we filtered out everything except the yellow line and calculated the heading angle between the robot and path center. This heading angle was then fed into a PD controller. The proportional term helped the robot respond quickly to deviations, while the derivative term stabilized the movement and reduced oscillations. Through tuning both gains, we achieved smooth and reliable path following performance. In addition to path following, we also developed a deep learning model for traffic sign recognition. By collecting images for stop, speed, and no sign conditions, we trained a classifier using the transfer learning. Once trained, the model was able to recognize signs in real time and provide probabilities for each category. Overall, Week 2 allowed the JetBot to interpret visual information, follow a defined path, and understand basic road signs, which are key components of any autonomous driving system. Week 3 expanded our system from local control to global navigation. We began by establishing communication between the JetBot and the overhead camera bot, allowing the JetBot to request images of its environment. To ensure accurate measurements, we performed camera calibration to remove radial and tangential distortion. With a calibrated camera, we used April tag detection to obtain the JetBot's real-time position, specifically its X and Y coordinates along with its heading angle. This gave the robot the ability to localize itself within the map, similar to how autonomous vehicle uses sensors like LiDAR or GPS. Once localization was in place, we moved on to global path planning. Using a probabilistic roadmap, we generated a network of possible paths and computed the shortest route from the starting point to the goal, which were defined by us. From this path, we extracted waypoints and developed logic to determine whether the robot should turn left, right, or continue straight based on its orientation. Week 3 completed the essential components of autonomous navigation, knowing where the robot is and planning how it should move through the environment to reach its destination. Together, these 3 weeks built the full foundation of our autonomous system, from motion control to visual perception, all the way to localization and path planning. With all these components in place, the next step was to integrate them into a single unified program. To show how each subsystem connects and how the robot makes decisions during navigation, I'll now pass it on to Akmal Hazrin, who will walk through our final flowchart and explain how everything comes together.
Now that we covered the full progression of Lab 1 through Lab 3, we can look at how all of these components come together in our final autonomous navigation system. Before the JetBot can move on its own, it first needs to understand where it is, where it needs to go, and how to react to what it sees. Autonomous navigation is not just about movement, but about making informed decisions based on sensor input and predefined logic. This flowchart shows the overall structure of our system and explain how different components work together to allow the JetBot to navigate the map autonomously in a controlled and reliable way. First of all, we start with the localization using April tag detection. The camera bot will capture calibrated image, which helps reduce distortion and improve detection accuracy. These images are then processed to identify April tag placed on the map or can also be known as reference point. Using the detect tags, the system calculates the JetBot's initial position and orientation relative to the map. This step is important because it gives the JetBot a clear and accurate starting point, which directly affects the accuracy of all future navigation and the movement decision. Then, once the starting point is known, that information will be passed into the path planning stage. In this stage, the system combines the camera image, pixel to real-world scale conversion, and the localized position to analyze the map. This allows the JetBot to understand distance and directions in real-world units rather than just pixels. Based on this information, the system will generate a safe and efficient route made up several nodes or waypoints. These nodes act as intermediate targets that guide the JetBot step by step toward the final destination while avoiding unnecessary or unsafe paths. After the path is planned, the JetBot moves into the execution and decision-making stage. At each node, the system determines appropriate action to take, such as moving forward, turning left, or turning right. The JetBot continuously follows the path plan while using its camera to maintain alignment and correct small deviations. This real-time feedback is important because it allows the JetBot to stay on course, even if there are slight errors or change during movement. At the same time, the JetBot also performs sign detection using the train model. This allows the JetBot to recognize and respond to different traffic-related signs on the map. If no sign is detected, the JetBot continues moving at its current speed. If a stop sign is detected, the JetBot comes to a complete stop for 5 seconds before resuming motion. When a speed limit sign is detected, the JetBot adjusts its motor speed accordingly. This behavior adds an additional layer of intelligence, allowing the chatbot to react dynamically to environmental cues rather than just follow the path blindly. Finally, after each action is executed, the system checks whether the chatbot has reached the next node in the planned path. If the node has been reached, the system updates the current node and moves on to the next one. If the node has not yet been reached, the chatbot continues following the path while monitoring signs and camera feedback. This loop repeats until the final node is reached, at which point the navigation task is complete. Overall, this flowchart ensures that the chatbot will navigate the map in a structured, adaptive, and reliable manner. That's all from our flowchart that I can say. Now, I'm going to pass to Matthew Choi for the demonstration.
For our team-defined task, we identified 5 essential capabilities that an effective autonomous system must demonstrate. These capabilities reflect the core functions used in real-world autonomous vehicles, and together, they allow the JetBot to operate intelligently in a dynamic environment. The 5 components we focused on were robot-to-robot communication using AprilTag, path planning, path following, sign recognition, and precise motion control using kinematics. Each one plays a critical role in how autonomous robot perceives, decides, and acts. Here is how each capability was implemented in our system. The first capability we implemented was robot-to-robot communication and localization. The JetBot communicates with the overhead camera bot to request an image of a field. The image is then processed to detect the JetBot's AprilTag, allowing us to find the real-time X and Y coordinates and heading angle of the JetBot. This step is crucial because the robot must know its exact position before it can plan any movement. Once the JetBot knows where it is, the next capability is path planning. Using probabilistic roadmap developed in week 3, the robot computes the shortest route from its current position to the desired goal. This includes identifying intermediate waypoints and determining the correct turning decisions needed to follow the optimal route. This provides the JetBot with a high-level mission plan, similar to how a self-driving car receives a navigation route from point A to point B. Next, the JetBot transitions from planning to execution through path following. Using HSV color filtering, the robot isolates the yellow line on the map and calculates the heading angle between its orientation and path center. A PD controller then adjusts the wheel speeds to minimize this error, enabling smooth and stable navigation even through curves and disturbances. This ensures that the robot stays on its intended path while still respecting the globally planned route. Along the path, the JetBot must also interpret visual clues in the environment. Using the deep learning classifier trained in week 2, the robot identifies stop signs, speed signs, or the absence of a sign. The model processes each frame in real time, and the JetBot adjusts behavior accordingly. This allows the robot to follow simple traffic rules, demonstrating perception-based decision-making, just like autonomous vehicles must respond to road signs and signals. Finally, all higher-level decisions are executed through the precise motor control and kinematics. This includes accelerating smoothly, maintaining straight paths using calibrated wheel biases, and performing accurate rotational maneuvers based on kinematic calculations. This foundational capability ensures that every decision made by the planning and perception systems is translated into reliable physical motion. In the next video, we'll demonstrate the robot finding its exact position using AprilTag detection, making a path plan, driving forward along the dotted yellow line using path following, stopping at a stop sign using sign detection, and then making a precise left turn using kinematics. The thing that makes this team-defined task meaningful is the JetBot's ability to complete all 5 tasks in one continuous script. The robot locates itself, plans where to go, follows the path visually, recognizes signs, and executes precise movement, all without human intervention. Through the past 5 weeks working on this project, we have gained hands-on understanding of how these components interact, and we've built a deeper appreciation for the complexity behind fully autonomous vehicles. And who knows, maybe one day, we'll be the ones that create fully self-driving vehicles. Thank you for watching our final demonstration.